Okay, so this is going to be the last lecture on filtration. What I will do is I will just do a quick recap of what we did in the last lecture. So, we were looking at developing an expression for what is the total pressure drop across a filter cake in the case of cake filtration, and what we did is we ended up with this particular expression. We ended up with showing that the total pressure drop delta P, which is summation of the pressure drop because of the presence of the cake and because of the presence of the porous filter medium is equal to the contribution that comes because of there is a term which is what is called as a specific cake resistance, and Rm is what is called as a filter medium resistance, and they are kind of defined in this particular way, right. That is what we had done in yesterday's in the last video lecture. And then what we did is we took the general expression and then we considered a case of a constant pressure filtration, wherein the objective is to relate the time of filtration and the volume of the filtrate that is collected during the course of filtration. So, we ended up with an expression which is T by V is equal to K C by 2 times P plus 1 over Q naught. Okay, that is what we had done in the last video lecture. As I mentioned, so one of the nice things about doing this constant pressure filtration experiment is that you can actually generate data with which I can say something about the cake resistance. Okay. And I had mentioned that you could do a series of constant pressure filtration experiments. So, what you are looking at is data from for different filtration experiments. So, test 1, test 2, test 3, test 4 and test 5 they have been done at different pressure drops which are basically indicated here. So, 6.7 all the way up to 49.1, and during each of these experiments you basically collect what is the filtrate volume that is collected and the time. Okay. Therefore, I essentially have T versus T by V data, and what I could do with this data is I could actually plot them. These are again for the 5 different trials. I have this is for trial 1 and the trial 5, right. And so, if you plot T by V versus V, I get a straight line with a particular slope and an intercept, and from the slope and the intercept data I can actually calculate what is Rm, which is the filter medium resistance, and what is alpha, which is the specific cake resistance. Now, for this particular example, if you look at how this Rm and alpha vary as a function of as a function of pressure drop, it turns out that both of them are not constant. Okay, which the fact that Rm also changes is a little bit surprising, but you could argue that look, maybe the pressure drop that is applied across the during the filtration process is so huge that there is some modification to the filter medium. That means there could be some pores that are clogged by the particles because of the higher pressure drop that I have applied. That is why you see some variation of Rm with respect to the pressure drop that I have applied, and similarly alpha, which is the specific cake resistance, also changes. Okay. So, the point that I want to make is that in general alpha can increase with delta P because most of the cakes that people deal with, they are to some extent they are compressible. Okay. And whenever you have a compressible cake, you will have alpha varying with delta P. For highly compressible cake, alpha increases very rapidly with the delta P, but you could have cases where there could be the variation may not be that steep, and you could also have cases where you have constant alpha as well. Okay. It depends on if you essentially if you work with conditions where my delta P that I have applied is smaller, plus if the slurry that I am working with is consists of rigid particles which do not kind of yield when you apply a particular pressure drop, I could assume that the cake is incompressible. So, most commonly what people do is people use experimental data and they fit an power law kind of a expression of this sort, where alpha goes as alpha naught into delta p s to the power of s, and depending upon what is the value of s. Okay, if it is closer to 0, it is if it is 0, it is incompressible, and if it becomes closer to 1, it becomes highly compressible. Okay, and for the example that we looked at, it turns out for this case the exponent s is about 0.26, which basically tells me that the cake that is being dealt with is slightly compressible, right. So, now that we have talked about the constant pressure filtration, we will move on to looking at constant rate filtration. Okay. In the case of constant rate filtration, what is done is the filtrate flows at a constant rate. Okay. Therefore, your u, okay, which is the superficial velocity, is constant during the course of filtration. Okay. So, as I had mentioned that during the course of filtration the cake develops, okay, because of the formation of cake there is going to be more and more resistance, okay, because of which ideally I should expect the flow rate to fall. Okay, the filtrate should start coming down at lower and lower flow rates. However, to maintain a particular constant superficial velocity or the flow rate of the filtrate, you carry out experiment by progressively increasing the pressure difference. That means what you do is because you want to maintain a constant filtration rate, you go on, you start with certain delta p, okay, and then you progressively go on increasing delta p, so that your filtrate flow rate remains constant during the course of filtration. Okay. So, and because your u is dV divided by A, and that is constant for the case of constant rate filtration, u becomes V by AT. Okay. Now, the expression that you see here is the expression that we developed for the delta Pc, right, that is a pressure drop across the filter cake. And now, if you know how delta Pc and alpha are related, and if I have some way of estimating what is delta P, then I can actually use this expression to relate the overall pressure drop to the time, right. So, in the case of constant pressure filtration, we were interested in looking at an expression which will involve the time of filtration and the volume of the filter that I am collecting. In the case of constant rate filtration, what I am after is to obtain the relationship that relates the delta P versus the time. Okay, that is what we are after. Okay. And it can be done in a fairly simple way. So, what we are going to do is I have this expression for delta Pc, that is delta Pc by alpha is mu u m c divided by A, and for u I am going to replace that u with. So, what I am going to do is I am going to write mu instead of u, I am going to write V by A times T, that is for mu, and I have m c, okay, divided by A is what I have. What I am going to do is I am going to multiply this by T and divide by T. Okay. Therefore, what I essentially have is that that is mu, and I have so we also know that m c is V times C. Therefore, what I am going to do is this, right. Let me just okay, I have mu here. So, that is and u and m c is V times C, right, and divided by A, and what I am going to do is I am going to multiply this by T and divide it by T. So, therefore, this becomes mu into V square by A square. So, I do not have to do this multiplied by divided by t, therefore, it becomes mu by v square divided by a square into c divided by t, right. Therefore, this becomes mu times c divided by t into v by a whole square, okay. That is what I have here, right. But now, if I, so we had said that there are empirical relationships that relate alpha to delta p c, right. So if I, so we saw that your alpha is alpha naught into delta p to the power of s, okay. Similarly, if you assume a similar relationship for alpha, so I could write alpha is equal to alpha naught into delta p c to the power of s, okay. I could do that. Therefore, all I am doing here is I am retaining delta p c here, right, and then instead of alpha I am writing alpha naught into delta p c to the power of s, right. And therefore, if I take alpha naught to the right hand side, so that I have alpha naught multiplied by mu c t, I can, what I can do here is I can multiply by t and divide by t here. Therefore, I have t that comes in the numerator, that is this t, and I have v by a t whole square, right. And so because delta p is equal to delta p m plus delta p c, okay, I can, instead of delta p c I can substitute it for delta p minus delta p m to the power of 1 minus s, because I have the power 1 here, right, and I have the power s here. So, therefore, if I take it to the numerator, this becomes 1 minus s. Therefore, delta p minus delta p m to the power of 1 minus s is equal to some constant times t, okay. And this constant k r essentially is alpha naught into mu c multiplied by v by a t whole square, and we know that v by a t is u. Therefore, your constant k r becomes alpha naught into mu c u square, okay. So, this basically gives us the relationship between how this how the delta, what is the delta p that I would have to maintain to basically achieve during the course of filtration, that is as a function of time, to basically maintain the constant rate of filtration, okay. So, that is the working equation for the constant rate filtration. So, just to sum up what we have seen so far. So, the total pressure drop delta p is delta p c by delta p m, okay, and it can be related to the specific cake resistance and the filter medium resistance, and for the case of constant pressure filtration you have T by V is equal to K C into V by 2 plus 1 over Q naught, and for the constant rate filtration you have delta P minus delta P m to the power of 1 over 1 to the power 1 minus S is K R times T. Now, so what I want to do now is to look at continuous filtration. So, I would we would like to develop, so we would like to consider the case of a constant pressure filtration, but however, instead of looking at a batch filtration process, that is what we looked at so far, but but a continuous filtration process. Before we do that, I just would like to kind of take an example of a rotary vacuum process and tell you a little bit about what continuous filtration is all about. So, in the case of continuous rotary filtration, okay, which is in this case it is a in this case the pressure drop, okay, that is supposed to be maintained constant, is done by applying a vacuum, okay. So, in this case what you essentially have is you have a horizontal drum, okay, that is the horizontal drum, and so what you are looking at is, if this is my drum, I am basically looking at it as a side view, right. So, therefore, I basically see a circle, that is what this circle that you are seeing is all about. Now, this drum, it actually has a slotted face, that means there are pores, okay, on the outer drum, and this drum rotates at a slow speed, okay, typically 0.1 to 2 revolutions per minute, and if you look at the diagram carefully, so what you do is this particular drum is immersed partially, right, in a slurry trough, and there is a feed that basically helps us with feeding the slurry that needs to be filtered into the slurry trough. Okay. And as you can clearly see that there is a portion of the drum that is immersed in the slurry trough, and over this slotted face, okay, you essentially have a filter medium, it could be a canvas, it could be kind of a cloth for example, and that covers the face of the drum. Okay. The entire drum is essentially covered with the filter medium, and so now so that is the outer drum, okay, outer drum, and there is also an inner drum, okay, and essentially the inner drum is actually it's a solid, it does not have pores. However, it has some slots, okay, which are essentially kind of shown in this diagram. Okay. These slots are essentially for carrying out the filtrate liquid, okay, into a rotary valve, okay, which is over here, right, and from there I can actually take out the filtrate liquid. Okay. And between the two drums there are these radial partitions, okay, these are the radial partition that I was talking about, okay, and they divide the space between the outer and the inner drum into separate annular compartments, okay, and each of this is connected through an internal pipe, that is these pipes, into one hole in the rotating plate to the essentially. So, all these are connected to the rotary valve, and from there the fluid is kind of taken out. Now, what we are going to look at is so if you look at so I am going to start with looking at this region A, that is we are going to look at the panel A that is shown here, okay, and this particular region is about to enter the slurry that is present in the trough. Now, as soon as this region enters the slurry, what is done is a vacuum is applied through the rotary valve. Okay. So, you have the capability of applying vacuum whenever we want, and you also have the capability of releasing the vacuum whenever we do not want it. Okay. So, now as soon as the vacuum is applied, a layer of solid builds up, right, because because you are applying a vacuum, right, and the liquid is sucked into the these radial tubes, okay, and whatever solids that you have in the slurry, they basically are deposited on the filter medium, okay, and of course the filtrate is collected. So, it basically it comes to the wall and is collected in a collecting tank. So, in this case, if you look at this particular operation, this is the rotary filter that we are talking about. It basically has two collectors. So, one is for the washed liquid, which we are going to talk a little bit later, and one is for the filtrate. Basically, filtrate gets collected in one container, and the washed liquid that is typically used for washing the filter cake is collected in a separate drum. Okay. Now, so as soon as this panel A leaves the slurry, it enters the washing and the drying zone. So, this is basically where the washing is done. So, you essentially have a spray that is basically sprayed onto the cake that is formed, and that ensures the removal of the residual filtrate liquid, and vacuum is applied to the panel from a separate system. So, essentially once you have used a washed liquid, of course, I would like to drain out whatever washed liquid that is also entrained within the filter cake. So, again I would have to suck all the washed liquid. So, for that you have a separate arrangement to do that, and once the washed liquid is drawn through the filter into the separate collecting tank, that is that is your washed liquid. Okay. That is a tank for collecting the wash liquid. Now, so after the cake of solid on the face of the panel have been sucked, so that means so the objective of this is to make sure that the cake is as dry as possible. So, once that is done, it basically leaves the drying zone, and once it leaves the drying zone, ultimately you remove the cake by using a knife, which is what is called as a doctor's blade, that is doctor blade, which is essentially used for scraping the cake that is formed on the filter medium, and then ultimately the cake is dislodged. Now, if you look at the operation, okay, for at any time, it is cyclic, okay, but that what I mean to say is that, so some of the panels in each part, okay, they in any given time, so they will always be so what I mean to say is that the operation of any given panel. So, what I mean by any given panel is each each compartment, right, okay, that is the each panel. Okay. So, for the operation of any given panel, it happens in a cyclic way, but since some panels in each part of the cycle at all times, the operation of the filter as a whole is a continuous process. Okay. That means, there are some panels in which the filtration is going on, there is some panels where there is washing going on, there are some panels where there is a drying going on, okay, and some panels where there is the scraping of the filter cake is going on. Okay. In that sense, so the whole operation occurs in a continuous way. So, therefore, what we can do is you can actually modify. So, if you look at the continuous filtration process, the feed, the filtrate, the cake, they all move at a steady and constant during constant rate during the entire course of filtration. So, if you consider the particular element, okay, of the filter surface, that means if I take different these panels, the conditions are not steady, but they are transient, right, because some are undergoing the cake formation process, some are undergoing the washing process, some are going the cake removal process. Okay. So, therefore, so for example, if you take an element of the filter cloth, okay, from the time it enters the pond of slurry, it undergoes the cake formation, the washing, drying, discharge, and each step involves progressive and continuous change, right. So, what we are going to do is to develop the working equation for the constant pressure filtration for the continuous filtration process. What we are going to do is we are going to start with whatever expression that we developed for the constant pressure filtration, that is T by V is equal to K C divided by 2 times V plus 1 over Q naught. We are going to modify that to essentially suit the need of the continuous filtration process that happens in a vacuum rotary filter, right. So, the way we do this is, so now this expression that you see, that is a quadratic equation in V, right. So, therefore, it has two roots. So, if you have ax square plus bx plus c, right, if that is your quadratic equation, we know that the roots are minus b plus r minus square root of b square minus 4 ac divided by 2a, right. Now, if I get the two roots, one of them is positive, that is what this root is, you can get that just by by this particular formula. Now, so once I have this, so I would like to because I know what is Kc and 1 over Q naught, I would like to substitute for these in this expression, and then I would like to reduce this expression from this into this. Okay. So, the way to do that would be what I can do is it's just a simple algebraic manipulation. So, what I can do is instead of 1 over Q naught, I am going to replace that with so I am going to write it as V is 1 over Q naught is mu square R m square divided by a square into delta p square, that is for 1 over Q naught square plus 2 times K c, I can write it as mu c alpha divided by a square into delta p, and of course, I have the t there, okay, that is to the power of 1 over half minus again 1 over q naught is mu r m divided by A into delta p divided by, instead of k c I have mu c alpha divided by A square delta p, right. Now, what I can do is I can do some simple manipulation. So, what you can do is I can multiply and divide this by delta p. So, therefore, what I am going to do is I have 2 there which was there earlier as well. Okay. I am going to write delta p here and then I am going to make this as delta p square, right. So, I have just multiplied and divided by delta p, that is the second term in the parenthesis. Then what I can also do is I can multiply and divide this also by mu. Okay. So, what I am going to do is again I am going to rub this off. Okay. I am going to multiply this by mu divided by mu, oops, sorry about that. Okay, divided by mu and I have 1 over 2, right. So, what I can do is, so I have mu square there, right. I have mu square and r m square divided by A square delta p square plus I have mu here, that basically makes it mu square, right. I have A and delta p square divided by A square delta p square, okay. And I am going to write 2 times, okay, delta p, that is this. I have c times alpha into t, okay, divided by mu whole to the power 1 over 2 minus mu r m divided by A delta p whole divided by mu c alpha divided by A square into delta p, right. So, I can do that. Now, what I am going to do is I am going to rub this all off. Okay, so, what I am going to do is I am going to take mu divided by A delta p as constant. I am going to take it out of the, so therefore, this. So, therefore, this becomes r m square plus okay, and this is also out, this is also out. Okay, so, that becomes 2 times delta p c alpha t divided by mu to the power of 1.5 minus, again I have taken mu A delta p outside, that becomes r m, okay, divided by mu c alpha divided by A square into delta p. So, I am going to cancel mu here, I am going to cancel delta p as well, and one of the A also gets cancelled. Okay. Therefore, now, so what I can do so therefore, essentially what I have is V is equal to A times I am going to write the second term first, delta p into c times alpha t divided by oops divided by mu plus r m square to the power of half minus r m divided by c times alpha, right, and I can take a to the other side, so that becomes divided by a. So, I am going to get rid of a here, right. So, now what I can do is I can divide by t, on both the sides. So, therefore, v divided by a times t becomes 2 times delta p c alpha t divided by, because I am taking it inside, there is a to the power of 1.5 there. So, therefore, it becomes mu into t square plus r m by t square, r m square by t square, okay, to the power of half minus r m divided by t whole divided by c times alpha, right, and 1 t gets cancelled here. So, I have this, okay. So, essentially that is what you end up with, right. So, that is this expression. So, it is basically a simple mathematical manipulation will essentially lead you to this expression. Therefore, what we have done is we have kind of converted this into v by a t is equal to 2 times delta p c delta p into c times alpha divided by that is mu t, right, that is this is mu here, right, mu t plus r m by t whole square to the power of 1.5 minus r m by t divided by c times alpha. Now, so in this expression this v by a is the rate of filtrate collection, right, that is the, because this is the volumetric flow rate, right, volumetric flow rate divided by a will give you what is the rate at which the filtrate is being collected. And in the case of batch filtration, a was the filtration area. However, in this case this a is going to be the area of the drum that is submerged in the slurry, okay. So, now what we are going to do is we are going to start with this and then do some simple manipulations. So, now that you have this expression, so I would like to kind of modify this expression to bring in the experimental variables that are typically used during the course of continuous filtration. That means, I would like to express this in terms of measurable quantities such as the rate of solid production, okay. So, this m dot, okay, m dot c is the rate at which so essentially we talked about m c being v times c, right, and if I want the rate of production of the solid which is m dot c essentially becomes v times c divided by t, right, that is what I have here. So, I would like to express this in terms of the rate of solid production. And if you look at the filtration process, so we worry about what is called as a cycle time T c, okay, and also the speed at which the drum is rotating, that is n, and of course the total filter area, right. So, that means I have the entire drum that is available for I have a drum area which is AT. However, only a part of it is available for filtration, that is what is A, right. Therefore, if the fraction of the drum submerged is f, okay, I can actually relate this, okay, as T by T c, right. That means that is the total cycle time and that is the time for which the drum is in contact with the slurry, and this essentially depends on the rotation speed, right, depending upon what is the speed at which the drum is being rotated. If it is rotating very fast, okay, that is the drum is in contact with the fluid for a shorter period of time, okay. However, it is rotating very slowly, that is the drum is in contact with the slurry for a longer period of time. So, therefore, so I have these expressions which is the fraction of the area that is submerged goes as A divided by AT, that is A is the area that is available for filtration and AT is the total area, and again I can express the same thing in terms of T by Tc, and of course the filtration time basically depends on is f divided by n, where n is the speed at which the drum is rotating. So, therefore, what I can do is I can use all this and then recast this equation into this form. Okay. Again it is a simple manipulation. So, if you are interested, if you can try and do it, so all you have to do is maybe I will just do that quickly. Okay. Okay, so I would like to develop this, right, that is what I am after. So, what I will do is I will start with this expression, right. I have V divided by A t. Now, what I can do is I can take this C to the other side, therefore, it becomes V C, okay, is equal to 2 A 2 delta p C times alpha divided by mu t plus R m divided by t whole square to the power of 1.5 minus R m divided by t, right. Now, I know that f is A divided by A t, therefore, A is f times A t, where A t is the total area. Therefore, I am going to replace A with A t times f, right. Now, therefore, I have V c by t, and we know that V c by t is m dot. Therefore, I have m dot c divided by A t. I am going to take f to the right hand side, therefore, and because I am going to, and of course, I have divided by alpha here, because I am going to take f inside the the bracket here. So, therefore, essentially I have 2 delta p C times alpha mu into t multiplied by f square, sorry, multiplied by, yeah, of course, f square plus R m into f divided by t whole square to the power of half. Note that I have f square here and of course, f square here, and to the power of 1.5, it basically yields me f that I have taken to the other side, right, minus R m into f by t, right. Now, okay, let me just now that is divide, of course, I have it, everything is should be divided by alpha, sorry, of course, I have t here, everything is divided by alpha. Now, so I know that because t is equal to f by n, therefore, t is equal to f by n, therefore, my n is equal to f by t, right. Okay. Therefore, what I can do is I have m dot c divided by A t is equal to 2 times delta p c alpha into mu into f by t into 1 over t, sorry, I have f here, right, that is f square, okay, plus R m into f by t whole square 1.5 minus R m into f by t whole divided by alpha, right. Now, f by t is n, okay, I have that here, and there is another f which basically is this f, and this f by t is n, right. So, therefore, this becomes n times Rm whole square, and this becomes n times Rm. So, essentially we have kind of recasted this expression essentially into this form. Okay, that is what we have done. So, now so that is the equation that we have recasted. Now, if you assume that you are working under cases where the filter medium resistance is negligible, therefore, I can essentially kick this term out and also this term out. So, the only thing that will be remaining is m dot divided by A t is equal to 2 times delta p times c into f times n divided by you have mu here, you have alpha here. So, therefore, that is what you will. Okay, I think of course, you had alpha here. So, therefore, it would become alpha divided by alpha square, because if I take it to the there is 1.5 there. So, therefore, 1 gets cancelled, therefore, in the numerator you should have alpha, right. That is what so that expression is right. Okay. And of course, I can say that if you are working with a compressible cake, I know that delta p is equal to alpha is equal to alpha naught into delta p to the power of s, right. So, therefore, I can replace for alpha in terms of alpha naught into delta p s, therefore, alpha naught remains in the denominator, and the numerator becomes delta p to the power 1 minus s. Therefore, so you basically have a framework by which I can actually find out what is the rate at which the solids are being deposited onto the filter cake, and for a case where both the cake resistance and the medium resistance becomes important, and I can recast this expression to really look at cases where the filter medium resistance becomes negligible, and of course, I can also kind of modify the expression to suit the need where I have a cake that is compressible. That means, I am going to I have taken the empirical expression that was developed to essentially get an expression in terms of expression that relates m dot to the coefficient that basically tells me something about how much compressible the cake is. So, the last topic that I wanted to discuss is to look at something called as a principles of centrifugal filtration. So, I mean, if you so the way the centrifugal filtration works is you have a container, right. Maybe you can think about it as a cylindrical drum, and it is basically rotated, right. And so, what is what you are looking at here, that is the outermost that is a inner surface of the drum, okay. And this inner surface of the drum of course would be it will be perforated, that means there are pores, okay. And on top of it you essentially put a filter cloth, and because of the centrifugal action, so what will happen is the slurry is kind of forced to come in contact with the filter medium, and the solids basically get deposited onto the filter medium, and that leads to the formation of a filter cake. And of course, you would have a liquid with the particles in the inner region of the the centrifugal filtration setup. So, if you think about this as a axis of rotation, so this R2 essentially refers to the inside radius of the basket, okay, or the drum that basically rotates, and Ri refers to the radius of the inner face of the cake, that is the cake is formed until this distance, and Ri is the radius of the inner face of the cake, and R1 is the radius of the inner surface of the liquid, right. And of course, if once the filtration is complete, if all the all the slurry is kind of consumed, so you really will not have this liquid. What will be left in the end would just be the filter cake, okay. And what you can do again in this case, I can, whatever basic theory that we have developed for constant pressure filtration, you can also apply the same kind of a formalism, but however you would have to modify that to suit the need of centrifugal filtration. Okay. Of course, there are some assumptions that are kind of important when you develop these things. So, we are going to assume that the cake is incompressible, the resistance of the filter medium is constant, that means so your Rm is not changing during the course of filtration, and we are going to assume that the cake is completely filled with liquid such that the flow is laminar, okay, right. So, you have all these assumptions that have gone in terms of developing these expressions. So, again we will start with the same working equation, the total pressure drop, that is delta P is delta Pc plus delta Pm, right, that is what we had mentioned, and this u, which is the superficial velocity with which the filtrate is flowing. So, we are going to write that as q by A, that where q is the volumetric flow rate of the liquid. So, essentially I have replaced u by q times A, therefore, I have q here, okay, and I have taken A to the in the parenthesis, therefore, because I have here, so I have A square here, and of course, I have divided by A that comes into the picture. Okay. And so, we are going to assume that area A, that is the area available for filtration, does not change with radius. Okay. Of course, this is only true if you are really working with a drum that is really large, and whatever filter cake that is formed, it is very thin. Okay. Only in such cases I can assume that the area A is constant during the course of filtration. However, you can of course modify your working equation to also suit the need where the area could also be changing as well. Okay. So, now if I want to solve this further, I should know what is delta P. Okay. And this delta P, which is the pressure difference that occurs during the course of centrifugal filtration, you can actually obtain by bringing this concept of hydrostatic equilibrium under the action of centrifugal force. Okay. What it essentially means is this, right, if you have a liquid column, right, and if I want to get what is delta P, okay, the pressure difference across, like say if I have a liquid column. So, if this is say position 1 and position 2, okay, we know that delta P is equal to rho g delta H, right, that is the that you kind of derive it from that basically is the hydrostatic equilibrium, right, if you have a vertical column of liquid. Okay. Similarly, if you have a fluid in a centrifuge, and if you are rotating at a speed omega, right, that is a rotation speed, and if rho is the density of the fluid, and I can actually, similar to relating the pressure drop to the difference across two locations, if I am at some radial positions r1 and some other radial position r2, the pressure difference delta P essentially goes as rho times omega square into r2 square minus r1 square divided by 2. You can actually derive this by doing a very simple force force balance. Now, so therefore, so I am going to instead of delta P, I am going to use this expression that comes from the hydrostatic equilibrium. So, therefore, from this I can actually get what is Q, that is what is the rate at which the filtrate is coming out from the during the from the centrifugal filtration process. Again a simple rearrangement leads you to this expression, and of course I have assumed that A is essentially a constant, right, that as I said will only be true if you are working with drums which are sufficiently large in diameter, or cases where the cake that is developed is very thin, right. However, if you have cases where there is a change in the area is too large, okay, if you cannot neglect the change in the area, all you have to do is you would have to replace this A square that you had here, right, with AL bar times AA bar, and the A that you had here, right, with A2, okay, that is the inner area of the drum itself, right. A2 is the inner area of the drum that is available for filtration, right, and AA bar is what is called as a arithmetic mean cake area, and AL is what is called as a logarithmic mean cake area. Okay. So, these areas better capture quantitatively how the Q changes during the course of filtration process. Okay. So, that is how one would deal with centrifugal filtration process. So, with that I would end the topic on centrifugal filtration, and you will have some assignment based on this in the in this particular week. Yeah, yeah, thanks.